Okay, we're going to be doing lesson 1.3 and 1.4 together. So, first what I've done is I've written two equations, just like we had before with substitution. But this time we're trying to find out if these are equivalent linear systems. So in other words, are they the exact same equation? So, in order to do this, what I'm first going to do is I want to line up my y's with my y's in a column, which is great right now. But I want to move my x's so they're in a column together, and my constant numbers so they're in a column together. So I'm going to rearrange these two equations. Equation 1, I'm going to put y first, x second, and constant third equals 0. And I'm going to do the same. So that's I've made no change if you notice from left to right. Still the exact same thing. Now, I'm going to put the y first, the x second. This technically says positive 9x. So I'm going to be moving plus 9x here. And this says subtracting 12 or negative 12. So I'm going to move that over here. And we still keep our equal sign in a column together and our zeros together. Okay? So we know they're both set equal to 0. So now what I've done is I've lined up my columns, y's, x's, and constant numbers. What I'm trying to find out is, are these the same equation? This is much like a fraction. Can I multiply one equation by a certain number to get the other equation? Okay? What can I multiply by, Michael?
3.
Which equation?
The first equation.
Okay, so Michael's discovered that I can either multiply equation 1, all of it, by 3, or what can I do to equation 2 to make it like 1? Divide. I can divide equation 2 by the number 3 to get equation 1. And I'm going to show how that works. So equation 1, y plus 3x minus 4 equals 0. I'm going to multiply. And whenever you multiply, you have to multiply both sides of the equation every single term. So I'm going to multiply y times 3, 3x times 3, negative 4 times 3, and 0 times 3. I'm multiplying every term there. So 3 times y is? 3x times 3 is? Positive or negative? Negative 4 times 3 is? And 0 times 3? Boom. And if we look, that is exactly what equation 2 is. So we have an equivalent linear system. Okay, now say I had to graph these equivalent linear systems. In order to graph something, we're used to setting it equal to what variable? Y. We're usually putting things in y equals mx plus b form, right? So what I'm going to do now is I'm going to set both equations, equation 1 and equation 2, equal to y. So we'll go back to their original ones. Go back to the original equations. Equation 1 was y plus 3x minus 4 equals 0. And equation 2 was 3y minus 12 plus 9x equals 0. So what I would like to do is I'd like to set equation 1 equal to y and equation 2 equal to y. So in order to do that, I need to move 3x and negative 4 to the other side. I'll end up with y is equal to 0 minus 3x plus 4, which is y is equal to negative 3x plus 4. On the second equation, I'm going to move my constant to the other side and my x to the other side so that I'm equal to 3y to start. I'll have 3y is equal to 0 plus 12 minus 9x. Okay, we'll equate that. We get 3y is equal to, and I'm going to rearrange the order. I'm going to put the variable first and the constant after, just so it looks similar to equation 1. So I have negative 9x plus 12. Okay, and finally, I need to get it equal to just y. So I need to divide both sides of the equation by 3, which means I have to divide every term of the equation by 3. I'm going to end up with y is equal to negative 3x plus 4. So again, you guys have noticed, which we already discovered, these are equivalent linear systems. But I want you guys to recognize something else here. I have y equals mx plus b. What is my slope in equation 1? Anyone know? Negative 3, and if we put it at a fraction, we could say over 1. What is my y-intercept?
4.
Okay. What about in the other one? Negative 3 over 1, and b is? What will these two lines look like on a graph? So, what that means is we found our y-intercept was at 4, we said. We said our point of intersection on the y-axis was positive 4. Is that right? Yeah. Positive 4 and negative 3 is the slope. Okay. So positive 4 is our y-intercept. And our slope was down 3 to the right 1. Down 3 to the right 1. Or up 3 and to the left 1. So let's draw this with a solid line. Here's our slope. We extend our line. Okay? And on the other graph, we discovered our y-intercept was 4. And we went up 3 to left 1. Oh, that's not perfectly drawn. Down 3. Oh, that's why the graph looks weird. Oh, guys, you should have pointed that out. I drew that slope wrong.
We went down it, yeah. We went down it 4 times.
Oh. All right, we fixed the slope of the first one. And our second one, we can do it in this giant red one. Our slope's like this. And like this. So, because these lines overlap each other, before a substitution we're finding one point of intersection. The points of intersection are infinite. Okay? That means they always intersect. At every single point, they're touching the exact same point. If the slopes were different, how many points of intersection would they have? So, let's put a little note here. Same slope and y-intercept. We'll put number of points of intersection, so P of I, infinite. Different slope. How many points of intersection if they have different slopes? Just one. And finally, same slope, and it should say same. Different y-intercept. How many points of intersection will the same slope, different y-intercepts have? 0. They will never cross each other. So, just an example of that. If I had another slope that was exact same as this, it goes like that. They're constantly beside each other. They'll never intersect. So there are 0 points of intersection between those. So when we go back here, we're looking for equivalent linear systems. It's important you recognize the slope and the y-intercept to tell if they're also equivalent. If they're both the exact same, then it means they're the exact same system. If the slopes are the same, they're not equivalent because there's no points of intersection. And if the slopes are different, they're not equivalent because there's no points of intersection.